nanohub.org.
Online simulation and more for nanotechnology.
Are you guys ready? Because today it's gonna be a little bit uglier than the other time, than last time. Okay, a little bit more difficult concepts, slightly more difficult concepts. But it's gonna be the last lecture that is like that, and then we'll slow down a little bit. Everything will start making sense. I mean, I can guarantee the lecture on Tuesday, every single word is gonna make sense. Now, the reason that I have these 2 lectures on Gaussian processes, actually 3 lectures on Gaussian processes, right? So this is still, we're still in Gaussian processes. The reason is because without that, the uncertainty propagation problems that we're going to be able to pose are trivial, right? So if you have a model and you have 4 or 5 parameters that you're uncertain about, this is not really a research level problem. You can probably solve it with what I'm going to tell you next week. But if you have things that are functions about which you're uncertain, you need this kind of tools to describe this uncertainty in the first place. So even though, you know, we went through these 3 lectures that are a little bit, let's say, more difficult than pretty much the whole course, they are the most difficult lectures of the whole course, in terms of mathematical content, at least. But you will see that they will allow us to solve some quite interesting, to actually pose some very interesting problems. I'll give you an example today of the kind of problems that we're able to pose right now. And because I'm going to be posing and solving these problems with different techniques, I will be repeating these things over and over again, and hopefully they will stick, okay? Anyway, so today we'll stay on Gaussian processes, probability measures in a function space, as we saw that 2 lectures ago for the first time. In the last lecture we discussed how you can take these probability measures and condition them so that they go through observations that you may have. But they're still very complicated objects. You need a lot of numbers, an infinite number of numbers to describe them. And today I'm going to tell you how you can actually reduce the dimensionality of these objects. And in some cases, you're going to be able to describe them with as few as 10 variables. In other cases, you're going to need 100. And in some other cases yet, you will not be able to do anything. You will have to keep the whole thing. But anyway, hopefully you will understand what I'm talking about as I go through it. And finally, what I'm going to do is introduce the first uncertainty propagation problem that we're going to see and solve with 3-4 different methods. In this class, we're going to solve this problem in 3-4 different methods. But I'm going to be able to just pose it today with the tools that we have so far. And so just to give you a reminder of why we're doing this thing with probability measures on function spaces. A lot of applications have inputs. Your models have inputs that are functions. Like, for example, in structural engineering, your input may be the acceleration of the ground as a function of time. This is, for example, an earthquake, right? So you need to be able to talk about your uncertainty about the earthquake, right? The shape of this function. This is the kind of uncertainty that you need to be able to describe. And then once you are able to describe it, the second problem is to propagate it through the structural model and come up with the fragility curves and so on and so forth. Again, for financial engineering, if you like, the models, you need some kind of model of the asset price as a function of time. Of course, no one can really predict what stock prices are. So you have to model this kind of uncertainty, and it's typically modeled actually with a Gaussian process or with a special covariance. And I'll actually have you play with that particular Gaussian process in the next lecture. But once you have this model, then you can ask questions like, what is the portfolio or the collection of assets that minimizes risk while maximizing expected payoff, and so on and so forth. Yet another example of a real model physical application with an uncertain functional quantity is flow through porous media or oil reservoir modeling, where the ground is actually the uncertain function. How the ground looks like is the uncertain function. And yet another application is numerical weather prediction, where you need to solve fluid dynamics equations plus some other coupling equations. These are partial differential equations, and you need to start them from somewhere. So you are uncertain about the initial conditions of this system of partial differential equations, and that uncertainty comes from the fact that you don't have weather stations everywhere. Right? So you're going to have to interpolate in between. And typically the way this goes is you say, before I see any data, I'm assuming that the temperature field is a Gaussian process. And then you start seeing some data, and you condition that Gaussian process on these observations, so that your uncertainty goes to 0 on the weather stations, but it grows away from the weather stations. And this is the kind of uncertainty that you want to propagate through the numerical weather prediction model. So you sample a temperature field from the Gaussian process model. With that temperature field, you start your numerical weather prediction model, you solve it, you find one path for the hurricane, then you sample another sample from the Gaussian process describing the initial condition of the temperature. You solve again, you get another path, you do that like 1,000 times, and then you get an envelope of paths, right? And I wasn't even able to pose the problem mathematically before I talked about Gaussian processes, right? Because that's the input to the whole thing. Unless you are able to describe the uncertainty in the first place, then what do you have to propagate? That's why we're doing these 3 lectures. And yet another form of functional uncertainty is model form uncertainty. So maybe your model has a constitutive relation, something that connects, for example, stress to strain, like Hooke's law, or maybe Hooke's law is not valid for your case. It's maybe you need a nonlinear law. Or here in this particular example from molecular dynamics, this potential energy may be something that you cannot know because you don't have the ability to, do the fully quantum mechanical calculations. So you're going to have a little bit of uncertainty about it, right? But it's a function. So you could, in principle, say, model your uncertainty about it with a Gaussian process, and then propagate it through the MD simulation and come up with uncertainties about the quantities of interest. Nobody has done that. So if you want to do that for a PhD thesis, be my guest. Somebody will have to get you funded for it, but it's actually a nice problem. Anyway, so to wrap it up, these are some of the things that functional quantities that you can now model with Gaussian process, model your uncertainty about them with Gaussian processes. That will be external forcing to dynamical systems, a function of time that kicks your system. Field parameters like the permeability of the ground or the elastic properties of a material and so on and so forth. Initial conditions of partial differential equations, which are functions of space, for example, boundary conditions of partial differential equations, physical laws themselves, constitutive relations, how to connect stress to strain, how to connect whatever, okay, whatever is your model. There is somewhere an assumption that connects, temperature gradient to flux of something. I don't know. All right? So it's very useful. I will give you now a model problem. That's a problem that we're going to solve in several different ways in this course. Okay, so it's a partial differential equation. This is a standard partial differential equation. It's called an elliptic partial differential equation. typically, I mean, we have a few typos here. We have a dot there. This is the divergence operator applied to A times X times the gradient of U. So this thing here, this rho is called the source term. Sometimes you may see a minus sign there, okay? But it doesn't really matter because you can absorb it in rho, so I'm not showing it. And you need boundary conditions to solve this equation. You can have Dirichlet boundary conditions. That is, you can perhaps know U on a boundary of your domain, and you can have natural boundary conditions on Newman boundary conditions, which basically describe the flux of U out of your domain. And this thing, A of X, is a parameter of your model, okay? Which you may not know. The source term is another thing that you may not know, okay, that right-hand side. The boundary condition is something that you may not know. The other boundary condition is also something that you may not know. Okay, and you can actually make it even more complicated by making the domain itself unknown. But we're not going to do that. Okay, like making the geometry itself uncertain. If this is a geometrical object spit out of a manufacturing process, perhaps it comes out a little bit different every time. And we could also model that, but it's a little bit difficult. Anyway, so all these things are uncertain quantities that are functions. And any of them could be, or all of them, are uncertain in applications. So some physical examples of this kind of model, where does this model appear? It appears in electrostatics, right? Where you would call U, for example, the electric field, A, you would call it electric conductivity, rho of X is any electric charge that you may have, right? And then your boundary conditions. And where could you use it? You could use this to detect, let's say, using just electric current, basically. You can use it to detect damages or faults in a piece of equipment, for example. Okay? But it's not that simple, but in principle, you could use that. It's the steady state heat equation. So this is what you would get as a steady state if you wait for a while. And in that case, that A of X would be the heat conductivity, yes, of the material. The rho of X would be any heat source you may have. And it's also an equation that appears due to Darcy's law in subsurface flow, where this U would then be the pressure and A of X would be the permeability of the material, and so on and so forth, okay? And, I mean, there's really a lot of applications in which this can appear. It's a ubiquitous law. Okay? Now, let's just concentrate on A of X. So let's say that we're doing subsurface flow, use the pressure. Rho of X is basically describes our injection and production wells of our oil reservoir. So rho of X describes where we're pumping water and how much oil we're getting out of the reservoir. And A of X is the permeability of the ground. How much oil can the ground hold, basically. And let's assume that we just don't know A of X, because rho of X is something that we control, right? We can measure the pressure on the locations of the wells, so we know rho of X. But A of X is the ground itself, which we don't know. So we don't want to model it. There are a few things that we know about A of X. First of all, it has to be positive. Why does it have to be positive? Because that's the definition of the permeability. It's a positive quantity, okay? We better create a model that imposes that. So since it is positive, we're going to assume that it is the exponential of another function. This is a very common thing to do. Okay, if you have a positive quantity, you say, okay, let me just work with the logarithm of that quantity. Okay, so I'm going to say that A of X is the exponential of an F of X. And now I'm going to model f of x as a Gaussian process. Why am I going to model it as a Gaussian process? Because if that's all I know about, I mean, if the only thing I know about a of x is that it is positive, then that's the simplest model you can use, right? It's just, it's the same thing as if you had a single random variable that you wanted to model, and then you had to pick a distribution about it. Why on earth wouldn't you pick a Gaussian as a starting point, at least? Okay. So when you have no data about the permeability, you just assuming that it is a Gaussian process, it is the exponential of a Gaussian process, makes sense. And then you can use the covariance of that Gaussian process to control how fast it changes. And if you are, you go and you talk to a geologist and you ask them, so how does that permeability field look like really? And you ask them questions like, is it continuous? And they're going to say, yeah, maybe. Okay, it's actually stratified, but let's say it's continuous because then it's too complicated. So does it have derivatives, this permeability field? And they say, no, it definitely doesn't have derivatives. It changes abruptly. So we may assume that it is continuous, but it's not really smooth. So you pick a covariance function that encodes that, right? That does not give you samples that are smooth. That covariance function would be, for example, the exponential, not the square exponential, just the exponential. Will give you continuous samples, but without first derivatives. And then you ask them questions about the length scale. So how fast do you think it changes? So is the length scale like in the order of millimeters? They say no, maybe it's higher. It's of the order of tens of meters. Okay, great. Then I'll pick this length scale. And then you ask them how much do you think it changes? And that depends on the kind of rocks that you have, right? So if they know that in this particular reservoir they can find 5 different kinds of rocks, then it can go from a certain value to a certain value, and then you can pick the variance of your covariance function according to that. So that's how they come up with that covariance. Actually, they do that. I'm not making it up, okay? That's how they do it. In case you were wondering. And now the other thing that you do once you have this prior probability measure on the space of A's, right? So you have you want it on the space of A's, but you work with F because F is the Gaussian process. So once you have constructed that, then you ask them, okay, do you have any data now? They say, yes, I went to the field and I drilled at 5 different locations. I took the rock out and I measured the permeability. And you're like, okay, tell me, what do you think is your measurement noise? Do you think you have measurement noise? Yes, I definitely have measurement noise. Do you know anything about your measurement noise? We're like, no, I don't know anything about it. Okay, but here's the data. So you get your data now, and your data consist of measurements of the permeability at 5 different locations. Okay, X and Y. You condition your prior Gaussian process on this X and Y, and you get a posterior Gaussian process. And then you ask them, do you have anything else? They're like, no, that's all I have. Okay, so here's the best model I can come up with for the permeability of the ground. And then you tell them, okay, now that I have that model, give me a couple of weeks, and I tell you the uncertainty you should have about the oil you're going to produce over the next year, let's say, right? Or if I have this uncertainty, if I'm able to propagate this uncertainty effectively, maybe I can tell you where is the best location to drill. You could do that. Questions? All right. There's only one problem. There are actually more than one problems. Yeah, so I just describe this with words, okay? So the easiest way to propagate uncertainty is to sample functions, evaluate your model, and look at the results, right? And of course, one of the problems is that your model may be very expensive, right? So if your model takes a week, then you cannot just sample the hell out of it, okay? And that's a problem that we're going to worry about in 2 weeks, Okay, but for the time being, let's say that you have a model that is moderately expensive. Let's say 5 minutes, okay, to evaluate it. That's okay. You can run it like 10,000 times or more. So let's worry about sampling the Gaussian process. To sample the Gaussian process, what we have learned so far is that you should really just pick a bunch of points, right? Pick a bunch of points on your on the input domain of the Gaussian process, any points you like, and then you look at the values of the Gaussian process on these points, and then because of the Gaussian process assumption, the distribution of the values of that function on these test points is going to be Gaussian, right? And that mean is going to be the posterior mean of the Gaussian process. It's a vector, posterior mean evaluated at the test locations, and this K is the covariance matrix, n by n matrix, and it's the covariance function, posterior covariance function evaluated at these points. Yes.
Is this the X that you were talking about the other day with the X star?
Yeah, that would be the X star, or more, anything you want. Okay. So I have built the Gaussian process with all the data I have, and I have a mean which could be a posterior mean if you have conditional data, and a covariance function which is a posterior covariance function if you have conditional data, and this M and that K are these quantities evaluated at these test locations.
So this F is by running the function, or
What was that?
these F values are by running the function, or
We have used the Gaussian process to quantify our uncertainty about that unknown functional quantity, and now we're saying let's just sample it at some points. Okay, just sample from this function at some points. Why do you need, why would you need that? Well, if you want to actually solve this partial differential equation, you better take a realization of A, right? You better sample A. So and you're gonna need A at a finite number of locations, at a finite number of X's. You don't need it everywhere, but you need it at a finite number of X's. And where you need it depends on how you solve this partial differential equation. Are you going to use finite differences? Then you need it wherever the finite difference method needs A. Are you going to use finite volumes? Probably need it at the centers of the cells. Are you going to use finite elements? You need it at all quadrature points of the finite element method. Anyway, if you have any domain whatsoever, you pick your favorite method, okay, to discretize that domain, your favorite numerical solver for that particular type of equation, and that numerical solver will dictate where you need to sample that unknown function, okay? And it will typically be either at the center of your discretization cells or at the quadrature points. If you have no idea what I'm talking about, I've probably not taken a finite element course, but that's fine. You need that finite number of points. That could be a lot, okay? So if you just take, let's say, a cubical domain and you want to do a discretization in spatial domain, right? Just a cube. And you want to discretize it, let's say, with 100 points per dimension, so that you have 100 by 100 by 100 grid. Then you're going to need it, and you're using finite elements, let's say, so that the function is only needed at the center of each one of the little cubes, the little square cubic elements. Then you're going to need 1 million. You're going to need to sample the function at 1 million points. Okay? And to sample the function at 1 million points, the Gaussian process, it's not actually possible. It's impossible. And the reason it is impossible is because the Gaussian process, in order to sample it, you need to build a matrix that is n by n, where n is the number of points where you want to sample it. So you're going to have to build a matrix that is 1 million by 1 million, and it's not sparse. Okay, so it's a dense 1 million by 1 million matrix. And, well, if you could even store that matrix somewhere with 64-bit precision, then you will have to take its Cholesky decomposition, which takes n to the cube. Okay? So forget about it. It can't happen. Okay? So it's not a good idea to just sample it with techniques that we introduced last time. And this is one instance of the curse of dimensionality. We're going to see more as we go through the course. Okay, but it is just one instance. So the question that naturally comes here in mind is there a way to reduce the dimensionality of the Gaussian process? So instead of, having to sample it at 1,000,000 points and having to build a matrix that's 1,000,000 by 1,000,000 and take its Cholesky decomposition, is there another way? And yes, there is another way, but there is a catch. Okay. Just to appreciate that, where this other way comes from, just look at that. So when you have a smooth covariance function that gives you smooth, nice, with big length scale samples, then there's definitely a way to reduce the dimensionality. I mean, even if you want to use in your solver like 1,000,000 discretization points, it's obvious that to describe these functions, you don't need 1,000,000 numbers. Probably need like 10, okay? But how are you going to do it? But of course, as you go to more and more complicated functions, as you make the Gaussian process less smooth, you're going to need more points, naturally. Yes, more variables to describe it.
Can you explain what is a smooth covariance metric?
A smooth covariance function. Okay, so last time I said that the regularity, actually I said that 2 lectures ago, the regularity of the samples you get from the Gaussian process is the same as the regularity of the covariance function. So, and there's a theorem that says that if your covariance function is continuous, then the samples you get are going to be continuous. If your covariance function is twice differentiable with second derivatives that are continuous, then the samples you get are going to have the same property. And if your covariance function is infinitely differentiable with continuous derivatives all the way, which is what I have here, because this comes from a square exponential, then your samples are going to have the same property. So as you go to more complicated covariance functions, this one, the Matern one, it's 2 times differentiable. Therefore, the samples you get are 2 times differentiable. And perhaps, for the physical application that you're looking at, this fits what you know about that field better than the, let's say, smooth field. And this is the exponential covariance function, which is continuous but nowhere differentiable. And this is the covariance function that they use in oil reservoir modeling to model the permeability, because the permeability of the ground can change abruptly as you go from one rock to the other rock. Okay, so it's not even continuous, but it approximates better what is going on than the smooth one. Anyway, the less smooth the covariance function is, the more variables you will need to describe that Gaussian process. Okay. And now we get to the main part of the lecture, which is how you actually do that. Okay. And it goes like that. There's a theorem called the Karhunen-Loew expansion theorem. And that theorem says that if you take any random field whatsoever, anything, it doesn't even have to be a Gaussian process, it can be written like this, okay? This is just what the theorem says. You can actually prove it. We're going to prove it, for Gaussian processes, but it holds for any random field. And it doesn't only tell you this, it tells you any random field, you can write it like that, you can expand it in terms of an infinite number of random variables size, right? So you have a random field, which is a probability measure on a function space, and the theorem tells you, well, you can describe that with an infinite number of random variables, okay? Not very useful, okay, but that's what it says. And it says that you can actually expand it in a linear basis, the coefficient of which are these random variables. It tells you more things. It tells you that this m of x is actually the mean of the field. Okay? And these basis functions are a little bit straight. Now, for a Gaussian process, the Caron-Loew, if the field itself is Gaussian, then the Caron-Loew theorem says that these coefficients are going to be Gaussian. They're going to be actually standard, normal, and independent. Okay, this is what the theorem says. If you don't have a Gaussian random field, then they can be dependent, they can be whatever actually. Okay, but for a Gaussian random field, they have to be independent. So that's what the xi's are for a Gaussian process. They're just standard normal numbers. Infinite of them, however. And now what is this guy? This square root of lambda and this phi I. So these phi i's are some basis functions. They're, which we're going to call eigenfunctions. And these lambdas are some values which we're going to call eigenvalues. And they're actually the eigenfunctions and the corresponding eigenvalues of the covariance function. So this equation that you see right here, it's basically a generalization of the matrix eigenvalue problem to covariance functions. This is what it is. So instead of the summation that you have in a standard, so you have like a matrix times a vector gives you lambda times that vector, okay? But here you have a matrix that has continuous labels instead of I and J, right? At the end of the day, we're going to discretize it, but this is how they are defined. And they're called eigenfunctions and eigenvalues. Now, to really understand what is going on, you need Hilbert spaces, but I'll just make a connection with discrete algebra, finite algebra. All right, so but let's prove it. Let's prove that if we take a Gaussian process, we can actually write it like that, where the psi i's are standard normal, and then the phis are the eigenfunctions of the covariance, and the lambdas are the eigenvectors of the covariance. And m of x is just the mean. For a Gaussian process, for a Gaussian random field, there's a theorem that says that in order to show that something is a Gaussian random field, as soon as, it is Gaussian, or as soon as all the joint finite dimensional distributions are Gaussian, which happens here because all the xi's are Gaussian, all you need to show is that the mean has the right form and that the covariance has the right form. So you compute the mean of this expansion, and the mean is going to be, the expectation operator is linear, so you're going to get this guy, and then you're going to get this. But the expectation of the size is 0 because each one of them is standard normal. So they're going to disappear and you're going to get m of x. So this construction has the right mean, has the mean of our original Gaussian process. And then if you try to take the covariance between an x and an x prime, so this is the covariance operator we introduced in the beginning of the class, at the beginning of the semester. It's the covariance between the function value at x and the function value at x prime. This is this expression right here, right? So if you take this now and you plug it in there and you plug it in there and you do the math, you're gonna get this. Because the xi's are independent, so whenever you have get xi I with xi j expectation, you get 0. Whenever you get xi1 square expectation, you get 1. Whenever you get xi2 squared expectation, you get 1. So at the end of the day, you're going to get this. Okay? So infinite sum, lambda I, phi x prime. And then if the phi and the lambda are the eigenfunctions and eigenvalues of the covariance function, then there is another theorem. Comes from Hilbert space theory, called the Mercer theorem, that guarantees that this sum is going to be your covariance function. So Mercer's theorem says that if you go and take K and you find its covariance and you find its eigenvalues and its eigenfunctions, then K can be written like that, using the eigenvalues and the eigenfunctions. Okay? Anyway, here's how the eigenfunctions look like for a square exponential. So the blue one is basically looks like a constant. The blue one is the first one, phi1, if you like. The green one is the second one, phi2. This is the third one. This is the fourth one. And then as you go to higher orders, you're gonna get more wiggles, okay? And now the Gaussian process, a realization of a Gaussian process is basically a standard normal times the blue thing plus another standard normal times the green thing times another constant, the eigenvalue, but it doesn't matter, plus another random normal times a red thing, and so on and so forth. Okay, so you have taken the random field and you're now explaining it with a series of standard normal numbers. Okay, and what we're going to do is we're going to truncate that at some point. This is how the eigenvalues of the square exponential covariance look like. So they start very high and they go down very fast. Okay, and because these multiply this expansion, you'll see that it doesn't really make sense to keep all of it. And this is where the dimensionality reduction is going to come from. And this is how the eigenvalues decay for different length scales. So the blue one is the smallest length scale, where you see that the eigenvalues start small and they never really go to zero, but they just stay flat. For a bigger length scales, the green one, you see they start a little bit higher and they go down slowly again. I mean, imagine this goes to infinity. Almost all the eigenvalues are very small but constant, okay? This is even higher. So the highest possible length scale is 0.5 and corresponds to the yellow one, and this is the one that decays the fastest, right? The next one is the purple one or magenta one. It decays a little bit slower than the highest possible length scale. And the bottom line is that the smaller the length scale, the slower the eigenvalues decay, and the more you would have to keep to get an accurate expression of the random field. Now let me show you something else. There's no reason why you should build this construction of on the prior probability measure, the one you started with. You can apply it after you see some data. So here on the left, I started with a Gaussian process with a one-dimensional input. I observed some data points, this basically, that one and that one on the top. I constructed the posterior Gaussian process, and then I took I found the eigenfunctions of the posterior covariance function, and they look like that. Okay, so they don't really look like the ones that we got for a Gaussian process with no data. But look at what happens for these what happens with these covariance functions. See where they are zero. They are zero exactly where I have observations. So the covariance functions know where you have observations, and they're like, you know what, I'm just gonna be zero there. Okay, because there is no variability at that point. Okay? Okay, and this is how it would look in 2 dimensions. Right, so if you consider a Gaussian process with a 2-dimensional input, x1 and x2, the first eigenfunction of the covariance function would look like that. The second one would look like this, but there are actually two that kind of look antisymmetric, right? These two have the same eigenvalue. And this is the third one, and then it goes like that. But this is without observing any data. If you start observing data, so if you add data, I conditioned the prior Gaussian process on 3 locations that you see as crosses there, and I took now the eigenfunctions of the posterior covariance. And then you see that the original they basically look like the original covariance functions, but they are distorted so that they go to 0 wherever you have data. Right? So look at the previous picture. So, do you see them? See how they're going to be distorted if I add data. They're basically being pushed around by data points. So there's a data point coming and saying, everybody should be 0 here. Okay, so just gather around me. All right. I mean, I have it here in more detail. Okay, so they get distorted so that they go to 0. All right, so this is the Carnot law of expansion. So we said that if you take a Gaussian process, it can actually be expanded like that, and the size, the coefficients are standard normal, independent, and then these guys come by solving this problem. And now the question that we face is that, well, we didn't accomplish anything because here we go to infinity. Okay? And what do you do about that? Well, but it goes to infinity, but we observed that these lambdas go to 0 quite fast. Okay? So after some point, it doesn't really matter, we shouldn't really keep summing things up because we're going to be adding zeros. So that's the idea. You need to truncate the expansion at a finite number. And the question is, how do you select that number? And there's another theorem, also from Hilbert spaces. And the theorem says that it says something about the variance of the field. So the theorem says that the variance of the field at a given point is actually the sum of all the eigenvalues. So if you sum all the eigenvalues, you're going to get the full variance of the field. So the way you select that D is by summing up to a given D so that you capture as much of the variance of the field as you like. Right? So you say, find me a D that gives me 95% of the variance of the field. And I'm going to ignore that 5%. Hopefully it's not going to matter in my application. Or give me the D that gives me 99% of the variance of the field. And the way you do that is like that. You sum the eigenvalues up to D. This is the variance you capture when you keep D terms in that expansion, and you want that to be 0.95 of the full summation, or 0.99 or 0.90, depending on, you know, how important it is for you to keep everything. How much time do I have? Oh, plenty of time. Okay, good. Any questions? Yes?
Do we know the infinite summations limit?
This is a very good question, all right? So obviously, this is also a garbage criterion because you need to sum the infinite up to all the eigenvalues. Now, in practice, what you do is you solve a problem that gives you the first 1,000 eigenvalues or the first 10,000 eigenvalues, and you say that's the sum. Let me just pick, you know, D so that I get up to 95% of the variance of that I get with 10,000 eigenvalues. All right, so you still truncate here, but to a much bigger number than what D is going to be. Okay? Yes?
Can you explain again? It was around your slide 27 or 28. I didn't understand when we start observing stuff, you said something that becomes 0 and the shape totally changes.
Yes. So, the way that I build this expansion is by looking at the covariance function of the Gaussian process, right? So, and in particular, these guys here are the eigenvalues and eigenvectors of the covariance function. I will show you in a while how exactly we get them. But they are related to the covariance function. Now, when you have observed data, the covariance function you should use is the posterior covariance function, okay? So the posterior covariance function knows where you have observations. And what's going to happen is that these guys are going to be 0 wherever you have observations. So if you have an observation at, let's say, x1, then this will be 0 at x1. If you have another observation at x2, then this will be 0 at x2. All of them will be 0 there. All right, so that there's no uncertainty added wherever you have, wherever you have observations. right? Otherwise, in any other place where these are not zero, then this will add something or remove something from the field. Okay, but wherever you have observations, they're not going to do anything. Any other questions? All right. This is the hardest part of UQ, is coming up with fields that make sense and describe your state of knowledge about the problem. Okay. And it's also the hardest to understand because it requires going away from the, let's say, traditional understanding of probability, which is in terms of frequencies. I don't talk about frequencies, I talk about probabilities as a quantification of our state of knowledge about something, right? So that's one thing. And it involves a little bit of math to get these things right, a little bit of Hilbert spaces, random fields. But hopefully, this is all the math it needs. I mean, up to this point, a little bit more, like a little bit of linear algebra to actually get it, okay? But what is the amazing thing is that as soon as you understand, as soon as you can articulate how things like your beliefs about the smoothness of the field goes into the covariance function, your beliefs about the length scales goes to the covariance function. As soon as you can understand this connection, all the rest, we have done it, okay? You just have to turn the crank and get this thing that gives you samples of the field, okay? So the important thing, which you need to know, the engineers in particular, is how to translate what you know to covariance functions. That's all, really. So it's extremely important to understand this connection than it is to understand the math. I mean, you need to understand this connection, and then to understand that, you probably need to use a package that will turn this understanding into a finite dimensional description of the random field using the Carnot-Loewe expansion. It suffices to know the keywords because such codes do exist, okay? But garbage in, garbage out. So you need to understand the first part, which is the most important one. This part, I mean, you can talk to me, you can talk to the 5 mathematicians that we have here, and we'll tell you how to do it, okay? You don't even have to put us on your paper because it's trivial, okay? We'll just tell you use this package, all right? But now this is a course, so I'm going to tell you how to actually do it, okay? It's actually a math, it can count as a math equivalent. So let's go through it, okay? So so now I'll tell you how we find the eigenfunctions and the eigenvalues of an arbitrary covariance function, okay? And we're going to use what is known as the Nystrom approximation. The equation that we need to solve is this one. It's an integral equation. It's called the Fredholm equation. Okay? So let me read it. You integrate kxx prime, you multiply there with the function, you integrate over x prime, and then that should give you lambda times phi, and you're basically looking for the lambdas and the phis that have these properties. So you're solving for these functions. Okay? Now I'll tell you how to solve the Fredholm equation. What you do is you go to the integral and you say, let me just do a numerical approximation of the integral. I'll approximate it with a quadrature. Okay, so you introduce a quadrature. A quadrature consists of a bunch of quadrature points and a bunch of weights, so that the integral is approximated as the sum of the weights times the function, the integrand, evaluated at the quadrature point. So the integral becomes a summation, and these are the quadrature weights and these are the quadrature points. Okay? So you get this. Instead of an integral equation, you get basically an equation that has a summation. Okay? And then you go here and you say, this equation is supposed to hold for every x, for every possible x, but that's probably too much. So let me just make it hold for the quadrature points. So I'll take these quadrature points, I'll put them there and there. okay, wherever x is. But I'll put an arbitrary quadrature point there. And when you put an arbitrary quadrature point, you get this equation. And now if you look at this equation, it's actually a matrix eigenvalue problem. So you have here a matrix, we're going to construct it, times a vector, it's going to be lambda times the same vector. And it looks like that, okay? So that K here is basically the covariance matrix evaluated at all the quadrature points that you have picked. This is the diagonal matrix that contains the quadrature weights, the unknown eigenvector, and that must be equal to lambda, the unknown eigenvector. So you basically just need the eigenvalues and eigenvectors of this matrix. Okay, so you find them with your favorite methodology. It's a symmetric matrix, symmetric positive definite matrix. So all the eigenvalues are going to be positive. Okay. Now, but you still have one more problem. So the eigenvalue problem is only going to give you the fees at the quadrature points, and you want to get the fees at all the points, right? So what you do is you have found by solving this problem the eigenfunctions evaluated at the quadrature points. Then you go back here and you say, now let me take this, solve for this here, move this lambda on the other side, solve for this, and then approximate this. So this is a way to get phi I, and then I'm going to approximate the integral again with a quadrature. So look at that. You solve that equation for phi I at an arbitrary x, and then there is an integral here, which you approximate again with your quadrature. And this, you know, this is just the covariance matrix, so you get this. And that's the approximation. That's the Nystrom approximation to the eigenfunctions. So it goes like that. You first discretize, you turn the integral into a summation with a bunch of quadrature points. Hopefully you pick a lot of them. All right? A dense set of quadrature points. You solve an eigenvalue problem there that's going to give you the value of the eigenfunctions at the quadrature points, and then you reuse this equation to basically interpolate the basis functions everywhere. Yes?
X be larger than 3?
Yes, it can be anything you want. So you have, but if it is larger than 3, you cannot use a quadrature rule, a conventional quadrature rule. Right? So in 1 or 2 dimensions, you can use standard quadrature rules, Gauss quadrature, Chebyshev quadrature, whatever you want. Okay? But in higher dimensions, these quadrature rules do not work, and you need to use other quadrature rules. And this is a second instance of the curse of dimensionality. And we're going to start talking about integration on our Tuesday lecture. Okay, so when X is higher dimensional, by high we mean larger than 3-dimensional, it's not trivial to do this because there are no good quadrature rules in high dimensions. Okay, but this is another topic. Now, typically in your applications where X is going to be, it will either be time, so there's just one dimension, right? If you have a function of time about which you're uncertain, X will be 1-dimensional, or it will be space, so 1, 2, or 3, right? You will have to go to applications that are a little bit more complicated. Like nuclear engineering, you probably have more. If you're looking at cross sections or various or what, I don't even know what I'm talking about. But I have seen the equations because somebody asked me at some point, and it looked like you probably need more than 2 or 3. Okay? Let me just say that, so that I don't embarrass myself in front of the camera. Okay? So, anyway, this is pretty much it. Okay, about the Caron-Lev expansion. The hard part, we're done with it. I have programmed it. Salar has found a very nice bug. And hopefully we have fixed it. Did you fix it? But anyway, they will not notice. We will we will fix it, and the next when you if you try to use it in your research, please pull the latest version. Okay, just use the version you have already pulled. The bug is in the Nystrom approximation, in the weights, if I remember correctly. But anyway, so here's how it goes. So we took the elliptic PDE. We said let's be uncertain about the conductivity field or the permeability field or whatever your application is. Let's be uncertain about A. A is positive, so let's model it as the exponential of something, and let's make that something a Gaussian process. And let's think hard about how we pick the parameters of the Gaussian process. The mean should be whatever we think about the trend of that particular thing, and it could be 0 if that's what we think. And then in that case, we're going to model the regularity. Whatever we think about the smoothness of A should go to K, and then whatever we think about the length scale of A should go to K, and whatever we think about the level of uncertainty should go to K. And then you're gonna go ahead and gather any data you may have consisting of observations of A at different x's, and you're going to turn the crank and get the posterior Gaussian process, and that's what you have here, the posterior Gaussian process that incorporates whatever you think plus the data. And then, that's an infinite object. You throw it away, you turn the other crank, that's going to give you the Karun-Love expansion of this field, which allows you to model this uncertainty in the function space with a finite number of random variables, and they're all very nice random variables. They're just standard normal random variables. So you do that, and this involves using the Nystrom approximation to find these guys. So of course you don't go ahead and program it yourself because there is code that does that. Okay? And then you go to the next lecture, which is how you can take this uncertainty, propagate it through the model, okay? With the simplest possible method. So that's what we're going to do next time.